Thank you, everybody, for joining the seminar this morning at the CHPC. Also, thank you very much to the people online. I always knew we were going to have a bigger online audience than maybe in the lecture venue here at CHPC, especially given that it's been hectic weather in Cape Town the last few days. We probably saw some of the biggest storms in May we've ever seen. So I'm just glad, Chad, that you could still make it to be on site with us today. I'm very pleased that we can welcome our MathWorks and Optimum colleagues here. So Chad Freer from MathWorks is based in Boston. We've met just now, and I also explained to Chad that the CHPC has had a long history already with MathWorks. I mean, just hosting a MATLAB license for our users is I think, the core thing that we already do. But we have a very good relationship also with MathWorks in terms of supporting our training programs. And that is why I'm pleased that we could also welcome you now for the first time to Cape Town and to this. So maybe just on Chad. Chad is a applications engineer at MathWorks. He's based in Boston, but he informed us that he's been heavily involved in high energy particle physics and CERN experiments. So that is your area of expertise. But in particular, he's got expertise in optimization, parallel computing, high performance computing. I mean, those are all the kind of things that we like to hear, that you're definitely at the right place if those are your expertise areas. And I think it is just appropriate for you to share some of your HPC background, but also the quantum computing focus. You said you will talk a little bit about this because it all forms part of what CHPC is mandated to do and deliver the service to our users. And of course, make it very specific then to MATLAB. Yeah. Thank you, Chad. The title of his talk is Accelerate and Parallelize MATLAB Code. Thanks, Chad. Over to you.
All right, so thank you for the introduction. As we said, I'm going to be focusing on parallel computing in MATLAB. So really what we're going to be talking about today is how to leverage your hardware. So that could be CPU or GPU computing, and then scaling that to HPC clusters. So the agenda for today, so I'm going to talk a little bit about parallel computing in MATLAB in general. So that's going to be the parallel language, so the parallel constructs that you use in MATLAB. Then I'll have a little bit of a section on NVIDIA GPUs, so how do you accelerate your code using GPU hardware. There's going to be a section on the MATLAB parallel server, so that's going to be scaling to multiple machines instead of a single machine. I have a little bit of section on how to work with big data, so what does big data look like in MATLAB in modern times, and then a quick summary at the end talking about some of the opportunities, resources, and trainings that we have. So just to start, I wanted to show this video, just getting the idea of what we're really talking about here. So the idea is if you're doing some code that's going to be running on multiple cores, when you're running, if you're running on something like a single machine, 20 cores, something may take a long time to run. So for example, you see this simulation is filling in here. It gets, a few percent of the way done. So here we're showing some simulation. It's 2% of the way done on 20 cores. If you run the same thing on 1,000 cores, so if you're able to scale that up, you can run the entire simulation. So the idea is how to get your stuff to run using your entire hardware so that you can either scale up the number of calculations you're doing or speed up the calculations that you're doing. So the idea is with an HPC cluster, you can power through something in a handful of minutes, whereas on a single machine, you may be stuck only a few percent and you may take an afternoon to run something. So that's the idea of what we're going for today. So I want to talk about how we think of parallelism from the MathWorks side. So when we advertise MATLAB, we advertise it as a multi-threaded tool. So what that means is when you have a machine, you have a CPU, it has multiple cores, MATLAB implicitly uses that. What that means is if you run a function, like let's say you do a matrix multiplication, it will it'll automatically use the cores that you have available on your machine. So if you have 24 cores on your machine, you don't need to do anything. It'll just automatically use that. That's going to be some implicit multi-threading. So you have one thing, you can be restricted to a single thread. That could be like a for loop. If you have something that is implicitly multi-threaded, like matrix multiplication, that's going to be using all the cores that you have available on your machine. That's automatically done for you in MATLAB. You don't need to do anything like you would in Python. The idea of the parallel computing toolbox and explicit parallelism is what we're going to talk about today, and that's where you're going to take code or functions that you've written and then explicitly pass them along to different cores so that you can scale up your workflow. And then that can be done in two different ways. It can be done in a thread-based way, which is you apply multiple cores and everything works in the same memory space, so you can have multiple tasks working in a process. Or you can do individual processes, whereas if something is completely separate from each other, you can just use a core for a single process, and you can do that process X number of times, where X is the number of cores. So this explicit parallelism, which is everything here on the right, is going to be what requires the parallel computing toolbox. So that's that toolbox that's on top of MATLAB, which allows you to explicitly use all the cores that you want. If you're doing some sort of mathematical function, there's a good chance that it's already implicitly multi-threaded and already takes advantage of it. And that would not require the parallel computing toolbox. That's just given for free in the MATLAB language. So what we're really talking about is this kind of explicit parallelism. I will mention, because we know MATLAB users often use toolboxes, that we automatically integrate this parallelism into many of our toolboxes. So I put a few examples here. The idea is if you're using this toolbox, you don't need to refactor your code in order to make it parallelized. You can use the functions that are already in those, and then you'd have an additional argument like a use parallel equal to be true. And so that would just scale those for you without having to refactor your code at all. It's just an additional argument. That's it. And it'll just speed up your code for you. You don't need to worry about anything. So you'll just use that toolbox. You use the parallel computing toolbox, and you just, without refactoring your code, just go straight for it. What I will talk about in addition to that is the actual parallel constructs in the language. So that's going to be actual code that you can write to explicitly parallelize your code. So there's the two main ones that I want to talk about. It's going to be par_for and par_feval. Par_for is just a parallel for loop, and then par_feval is what we call asynchronous, and that means it's going to be running tasks in the background, and that allows you to change your workflows in certain ways to take advantage of the hardware that you have. So I'll start with a par_for, the simplest example. Here we have on the left a typical MATLAB code, and we're just going to be doing some iteration. And so you're going to do a for loop. You're going to run through 5 iterations. And what MATLAB will do inherently with that code is it'll use one core, and it'll just run them iteratively. So it'll just run 1 through 5. The idea with parallel for loops is that instead of just running them serial, we want to spread them across the workers that you have, so that way the total time gets reduced. So here you would see that it takes 5 times the iteration speed. Here, since it's split up among the workers, you can see that the actual total execution time goes down because you're able to split that execution down. Now, again, one important thing that we have with a lot of our tools is that we don't want you to have to refactor your code in order to use these tools. So the idea is that you can basically take the code that you have, which is a for loop, and if they're independent of each other, convert that to a par_for loop. So the idea is that there's a simplistic way to do this. So here, again, just showing what that actually looks like when you actually execute this type of code. What it does is it splits up the work along the workers that you have available. As soon as that work gets done executing, the next iteration comes in. So it's basically more optimized to the hardware that you have available. And again, it'll just run through all those iterations, and then it'll return the result to you at the end. So here you would be able to display whatever you've done through your parallel calculation in the exact same way that you would using typical MATLAB code. So one thing that is particular about par_for compared to for loops is because you're doing this in a parallel way, that doesn't means that if one iteration is dependent on another iteration, a parallel for loop may break down, right? Because that iteration may not be complete by the time the other one is going through. So, for example, you can do something A of I is dependent on I, but you couldn't do something like A of I is dependent on I minus 1, or the last iteration. So what we have in MATLAB code is if you do something like that, our code analyzer will highlight that for you. So you would say, hey, look, you're trying to do a par_for loop, but the iteration that you're calculating is not necessarily going to be available to you in this parallel for loop. So it highlights this as a code that could potentially break. So we have these kind of things highlighted of when and where you can use par_for when in comparison with for loops. The next thing that I wanted to talk about was par_feval. And the idea of par_feval is to run asynchronously. What that means is that you're going to execute something, and you're going to have that thing executing in the background while you can continue to work. So the idea is here I'm going to just create a parallel pool of threads. So I'm going to prepare my cores to be working. And then I'm going to run some function, and I'm going to run some function in the background. So here I'm just running my func, and what that does is it puts that function and it's running on a core in the background. Now, the important thing to do when you do par is that you can now still interact with MATLAB. So that function can be running in the background, and you can still do stuff in your MATLAB client. So for example, if you have some long-running function that may take up a few hours, you can run that in the background, and then you can still interact with MATLAB in the meantime. So that allows you to actually run things that are a little bit more complicated or a little bit longer running without actually fully blocking what you're doing. And so the idea is you can also do that multiple times. So if you have 10 cores, you can run 10 different functions in the background. And you can let them run for long periods of time. And then what you can do is you can collect the results at the end. So if you'd like to wait for that function to run, you can just do f.wait. Or if that function is completed running, you just collect the outputs of that function, and then you can return to any sort of post-processing or plotting that you want at that point. So again, the idea is to just offload that work into the background. So here I'll show a little example of what that looks like. So here we have just a simple for loop. We're going to do 5 functions. So here we're just putting five functions to be running in the background. Here we're going to do some criteria. So if we're looking at some random number, and if it goes over a certain number, then you can stop the iteration. So here you can basically queue up 5 functions. It splits up the work along the workers that it has available. And then it collects the results, and you can check some criteria, for example, and you can keep running until some criteria is met. So we call this the needle in the haystack problem. So if you don't know when something's going to happen, you can just queue up a bunch of functions until that eventually happens. And then once that happens, you can cancel all the rest of the results and then move forward with your work. So this allows you different types of specific workflows that may or may not have been possible if you were just iterating infinitely. So just to summarize briefly before I move to the next topic is these are the two main, there are other functions that we have available, but these are the two main functions we talk about with Parallel Computing Toolbox, is this par_for and par_eval. Both of these are designed to help you run computations using all of the cores on your machine. We also can scale this to the parallel server, which I'll talk about in a little bit, but this is basically to give you distributed computing on your machine. Par_for is the simplest method. So usually what you can do with par_for is just take a for loop and turn it into a par_for loop, and then that spreads it across the hardware resources that you have. But that blocks MATLAB. So you have to wait for that par_for loop to complete, just like you would a for loop. Par_eval is a little bit different. We call this asynchronous. So this allows you to run things in the background. This allows you to make a little bit more complicated workflows. So you can pipeline things into the different resources that you have and continue to do other things while you're waiting. So this gives you a little bit of freedom in how you want to run. I'll talk a little bit about GPUs. So GPUs are accessible through the Parallel Computing Toolbox again. As of right now, we currently only work with NVIDIA GPUs. We're working about potentially working with ARM in the future, but as of right now, we're working with NVIDIA GPUs. And we provide a few constructs into how to manage GPU resources. So for example, if you have a GPU device on your machine, you can effectively just look for this GPU device count. So here I see I have 4 CPU cores and I have 1 GPU available on the machine that I'm running this on. And the idea behind our GPU functionality is that, again, we don't want you to have to refactor your code. So if anyone's worked in GPU in other languages, often you have to write CUDA code, and that's basically you have to write kernels that would function onto those GPUs. So any function that you have to translate into some sort of CUDA function that can run on your GPU. What we've designed from our side is that you can basically just take constructs and apply them onto the GPU, and they'll run without really changing. So here I have some function that I've written. I've just called it some complicated operation, and it's just a bunch of mathematical operations. If I want to, I can run this on the CPU. I just take some array and I throw it on the CPU. To do the same thing, I would just take it and cast it onto a GPU array. So I just take this matrix and I put it onto a GPU. And then when I run, I do the exact same call. So I don't have to refactor code. I don't have to change what I'm doing. I just call it on a GPU array. What that does is it pushes it off, that calculation off to the GPU. The GPU will run it. And then when you want to, you can collect the result, and then you can compare. So here I did some complicated operation on a very large array, and you see that my CPU took about 5 seconds, but my GPU blew through it in a fraction of a second. So you got good speed up. You didn't have to refactor your code. You just changed the way that you changed the function call. So the idea is, again, making it simplistic for the users. So that's the idea behind a GPU. Just like we have parallel tools incorporated in toolboxes for PCT, we have the same for GPU. So here I showed an example. Here you're running some machine learning training, but you want to actually change the environment. So you would just say, hey, I'm using a GPU environment, and then that training is then broadcast onto the GPU instead of the CPU, trains the exact same way. You don't need to refactor what you've done in that toolbox. You just change the call. So just like the use parallel drop down for normal toolboxes, we have a lot of plugins for GPU for different toolboxes. One additional feature that's on a newer versions of MATLAB, so this is released in 2025A, so this is somewhat new, is partitioning. So if you have some parallel pool, which means you have some resources available, you can also make partitions where you can connect different hardware. So for example, here I want to split my parallel pool into GPU workers and then CPU workers, meaning I want to run some functions on the GPU and I want to run different functions on the CPU. So this way I can pipeline my workflow to take advantage of the hardware that I have available without overutilizing the GPU or underutilizing the CPUs. So the idea here is I have 4 workers, but I have 1 GPU. So I want to actually put 1 worker, 1 CPU to work with the GPU, and the other 3 CPUs, I want them to do other things. So here I can fully take advantage of my resources by partitioning these into 2 different little pools, and I can run my GPU functions on the worker associated with my GPU, and I can run some completely different function on my CPUs. So this allows you to make some more complicated workflows where you can take advantage of all your hardware resources and have high utilization on not just the GPU, but the CPUs at the same time. So here, this allows you to get a little bit more pipelining, a little bit more utilization out of your hardware. So the next topic I wanted to talk about was parallel server. So we've talked about parallel computing toolbox. That's scaling up on 1 machine. Parallel server is about how do I take MATLAB code and scale it up to many machines. So we want to take it to arbitrary scale. Maybe instead of just 24 cores on a machine, I want to run to hundreds of cores or thousands of cores. Or I want to run on very large memory. This is done with parallel server. So again, just like I showed this video in the beginning, the idea is this parallel computing toolbox allows you to run to maybe 20 cores, or if it's a small, a larger machine, maybe 200 cores. But what we really want to do is run to thousands of cores, and that's what takes this parallel server. There's very few machines that have thousands of cores. How do we get to that level? And that's through parallel server. So again, what we wanted to do is we wanted to make it somewhat simplistic, so you don't have to refactor your code. So the idea is what you're running with the MATLAB parallel computing toolbox on this machine, we want to take it so you can basically just offload that code onto multiple machines. So that could be an HPC cluster, it could be the cloud, it could be clusters with GPU resources, it could be clusters with just multiple CPUs, so large core count machines. But the idea is that without having to refactor your code too much, we want to be able to scale to these larger resources. So I'm going to go through a little bit of what this can look like. So the function I want to talk about is called batch. Again, this is just an asynchronous function. So the idea is you want to have your code and you want the actual execution to be done by a certain set of resources without having to block up your actual MATLAB client. So the idea is if you have some function and you're connecting to some HPC resource, so this could be like CHPC resources here, you would effectively just connect to this cluster and then batch up the function that you want to run. So here I'm just doing a batch command. I'm connecting to the cluster of my choice. This could be CHPC in this case. And I'm going to run my function and I'm going to run it with 1,000 cores. So the idea is I'm going to have my machine, I'm going to offload this into the cluster, and it's going to run all of these on the cluster without me needing to connect. So my function gets passed along to the head node. So in this case, in CHPC, you have a PBS cluster. You would pass this along to the PBS cluster. It's going to get those resources for you. So now it's going to be looking for 1,000 cores. Once it gets those 1,000 cores, it's going to run your function. Let's say you're running a par 4 loop. You can run a par 4 loop in this case with the 1,000 cores that are available to you. And at this point in your code, your machine no longer needs to be connected. So this is now entirely running on the cluster. The cluster is going to handle this entirely for you. Your client machine doesn't need to be connected still, right? So you can take this, if you have something that runs on, a week, you can put this, run it on the cluster, and it'll run in the background while you go doing other things. So once that's done, the function will collect its outputs. Here you can either store it to some local storage on the cluster, or if you'd like, you can draw it back into the client machine that you were working from. So here you can grab the results, and then you can do whatever sort of post-processing or plotting that you'd like. So again, the idea with this workflow is you have some very complicated or long-running function. You can offload it to resources. It'll run on those resources. You don't need to stay open with your client machine. It can run as long as you'd like. Then you can either store it locally on that cluster resources, so store it in some sort of local storage, or you can bring it back into the client and then do whatever post-processing there. But the idea is that all the work is being done by the cluster resources rather than forcing you to stay on whatever machine that you're on. Well, in terms of the actual license structure, from our side, we try to make it as easy as possible. So whatever you're running on your machine, that be MATLAB, whatever toolbox, and then the parallel computing toolbox that you need in order to run this parallel constructs, that is going to be on your side. From the cluster side, you just need to have parallel server available. So when your job comes in, whatever toolboxes are running from your side, we'll open those up on the cluster side, but the cluster side will just require that parallel server license. So the license structure is a lot easier than trying to scale this up and taking X number of licenses in order to do that. Another new feature that we have in 2025 is the parallel pool dashboard. And the idea behind the dashboard is how to help you develop and debug parallel code. So with parallel code, it's sometimes hard to see what's going on under the hood, how your resources are actually being used and what's going on. And this parallel pool dashboard is designed to help you understand that. So for example, here I have a job with a few workers. And the idea is the blue can show me what's actually operating, and the purple, for example, shows me when I'm transferring data. So here I can basically see, what are my workers doing? Are they doing some sort of operation? Are they doing some sort of data transfer? Or are they idling out? If I see a lot of white space, then I know when I'm developing my code that I have actually pretty low utilization. If you see that these white spaces are basically filled in, then what you see is that you have very high utilization of your resources. So this tool is basically to help you track the amount of data that you're reading in and out, and then see how much time each of your workers is processing their code. So for example, you may have a lot of time that's in a data transfer. This will help you see what that's coming from and why that's happening. So this is basically just to help you along in that design and development process. Especially when you work with parallel code and you're working with large data, it can become very confusing, what step you're actually getting stuck on. I will say every kind of cluster has their own different environment and scheduler. We have made it so that we can integrate with whatever setup that you have. So for example, if you have cloud, we can support that. If you have clusters, we can support that. We do cross platform. So if you're on Windows machines but your cluster is Linux, that's fine. There's no problem that this all works smoothly. And then we also work with whatever third-party scheduler you have at your cluster. So again, CHPC has PBS, so we can integrate with that, and the parallel server will work directly with your scheduler, so you don't have conflict for hardware resources that you would if you had to do your own schedule. What this looks like for the user is once we have that set up, you have this processes and threads that would be your local machine. You would just have this additional profile in your MATLAB, which would be, for example, the CHPC cluster. So you would just connect to that on your MATLAB GUI, and then you'd be able to run on those hardware resources. I think in the case that you guys have, you'd actually SSH in the machine and then connect through some config cluster command. Since the world is moving into big data, I wanted to have a few slides on how MATLAB can actually help you treat that. We're getting to bigger and bigger data, so we're talking about now analyzing terabytes to petabytes of data. The problem with that is that that usually does not fit on local machines, so you have to have some more clever ways to analyze that. So we have some constructs that help you kind of use specific ways to deal with data in order to handle not being able to fit into your RAM. So one of the things that we use is called a data store. The idea behind a data store is if you have a very large data set and you need to read it in, but it's larger than your RAM, what it'll do is it'll read it in chunks at a time so that you can operate on an individual chunk, save the output of that, and then read in the next chunk. So that prevents you from overloading your RAM. So the idea with the data store is, let's say you have a bunch of CSV files, you can just collect that all into a data store. It'll say, okay, here are all the files that I have. I'm reading in almost 90 files. The idea is when I then operate on that data store, it'll read it in just a chunk at a time so that I'm never actually overloading the RAM that I have in a given moment. And so that's the idea, is to just chunk your data in efficient ways so that you can actually scale to amounts that you would not normally be able to do. So for example, if I use a tall array with the data store, I can call this tall array on the data store, and let's say I just want to do the average of whatever numbers are in this data store. Okay, but my single machine memory is only this chunk here. So what happens is that the tall data store will actually read this chunk, operate on this chunk, then move to the next chunk to do the same operation, and then iterate through that to take advantage of all the cores that you have to do that calculation as fast as it possibly can while fitting into the memory constraints of your hardware. So the idea is to power through that and it iterates through as it can, storing whatever memory you have allowed it to do at the time. So if you have only 2 gigabytes of RAM available on a given core, then it would only read in that chunk, that small chunk at a time. So the more RAM you can give it, of course, it can go faster, but it can work with whatever constraints you have in terms of the hardware. And then at the end, similar, you would just gather the results. So you would let it calculate through everything and then just gather the results at the end and be able to do your post-processing. In a similar way, we allow this to scale with parallel server. So if you have not just multiple cores, but multiple servers, we can do a similar type of command where instead of just working on a single machine memory, you pass this to multiple machines, and it'll iterate through them separately and then gather the result at the end for you. So for example, here I'm doing a 2-node. Instead of just running through on one machine, it runs through both machines at the same time, and then it gathers the results at the end. So here I can maybe have 3 or 4 servers, and I can calculate through very large data sets much faster. So the idea here is if you're moving into that terabyte, hundreds of terabytes, or even petabyte range, this will allow you to scale out those calculations. To actually do them, it'll just have to require a little bit more hardware resources. So as we move into the larger data set realm, calculations like this become more important as you need to have access to calculations that do very large memory. So a few summary slides, and then I'll leave some room for questions, and then maybe 5 to 10 minutes at the end just for quantum. But just to summarize, the Parallel Computing Toolbox gives access to your full CPU and GPU resources. So the idea is if you have PCT, you can use everything that's on your machine, right? So if you have an NVIDIA GPU or if you have 24 cores on your machine, PCT allows you to scale to that entire set of resources. The idea is parallelizing in MATLAB should not require you to totally refactor your code. It should kind of fit into what you're doing. You can either use parallel or use something like a for loop to a par for loop to take advantage of those resources. And then with parallel server, you can scale that to multiple machines. And again, that allows you to push your code to even more resources using whatever resources you have, in this case, a CHPC, which has thousands of cores available to you. I wanted to highlight that we're here to support you. So we have training sessions available. We have training sessions specifically for parallelizing your code. So I'll show you a little bit about that. But there's also tons of documentation for examples online. So if you go to the Parallel Computing Toolbox and just Google Parallel Computing Toolbox, you can go to our documentation. We have tons of examples for you. You can take the code and get started from there. So it's really easy to get started. You can just copy and paste a lot of our code and then fit in your functions into those examples. And then also, we're happy to help you debug. So my job is literally to jump on calls with people, and then I can help you develop and debug your code. So if you have questions or don't understand how something works, we can just jump on a call and figure that out on the fly. So we're happy to jump in and support you from that side.
The one question I actually had was the training
Yes, yeah.
Because I can imagine if somebody is now confronted with what you showed now, relatively quickly, they might be looking for where do I...
Yeah, so one of the big things that we have is called this Accelerating and Parallelizing MATLAB Code. This is a 2-day training course. So the idea is, first of all, how do we make sure the code is running efficiently? So if you're writing in MATLAB, are your MATLAB functions written efficiently? Are they taking advantage of your resources? So that's going to be using the profiler, which will basically help you see if you're using the resources that you have available. You can also generate MEX files, so that could be running C++ code if you're worried about performance. We'll move from that into parallelizing computation, so that'll talk about par4, par-feval, some of the functions that we talked about today, and then how to offload execution, so that's going to be that par-feval and batch functions. The second day of that training, you'll actually work with the cluster, so we make a little Slurm cluster, and that you can actually run on that Slurm cluster and offload calculations under that. The second half of the second day is going to be GPU computing, in which case you get access to some NVIDIA GPUs, and you can run some GPU array functions and see how that speeds up different parts of your code. So this is a really nice 2-day training course. You basically hop online, and we guide you through a lot of these topics. So that's number one. We also have a separate 1-day training course, and that's processing big data with MATLAB. So this is about creating those data stores, working with those tall arrays, and really trying to offload this execution of large data sets. So that's a whole day training course. Both of these are very nice. We also have in the online suite just self-run training courses, so you can just hop online and you can do the self-guided trainings. Those are only a few hours, but it guides you through the basic premises of parallel computing.
One or two questions, maybe not directly to this, maybe just a more general question. There was people just asking whether this presentation will be made available, and I maybe just can confirm to users that we will edit this video into a YouTube video. We've got a channel on Nikki's got a YouTube channel. We will put it on there. So what I will do is I will share it again to the mailing list, to just for those that missed this completely. There's a question actually on quantum, but maybe we should wait for your quantum part, because they want to ask whether we have resources for quantum machine learning, but I will get to that one.
Okay.
You have spoken. Then there's a question, I've not read it yet. It says, I'm running script with a set of first-order ODEs. I'm assuming I cannot use par4 to reduce the... Maybe you can read it yourself.
Okay, yeah. I'm running a script with a set of first-order ODEs. I'm assuming I cannot use par4 to reduce the simulation runtime to each iteration is dependent on the results of the previous iteration. Yes, so there's a few things to think about here. Often with ODEs, they're implicitly multi-threaded, so that they often run faster if you give them more resources. So sometimes if you're using a par4 loop for something that's implicitly multi-threaded, you might actually see your code performance degrade. So you want to make sure that you're always giving the resources available to multi-threaded operations. And then in the case where they are dependent on iterations, yes, that's a case where you cannot use par4. Unless you found some way to, simplify or estimate the previous iteration. So in that case, you would have trouble if you're running ODEs that are completely dependent on previous iterations.
Did you see that you can use other options besides par4? I'm not sure if you saw that.
I think that's associated with the same question. So yeah, again, just check. I think if you give something a single core and then give us a second core, you'll see that a lot of operations like ODEs are implicitly multi-threaded, so that this par4 is not necessary for those type of functions. But that's something we can check on or call on.
Yeah, no, thank you for the online question. So maybe before we talk quantum, maybe just a few thoughts. I think when we discussed what Chad will present, he indicated that there's some focus on quantum computing support and so on as well. You would first want to ask a question?
Can I ask about the training?
Yeah.
Why isn't it done on the CHPC or the local machine? Because I don't want to play with the Slurm cluster.
Okay. Well, so that training is a MathWorks supported training, so it's generalized. So that is just made available for anyone, and we use our Slurm clusters internally for that. For training on CHPC, we could either design something with you guys or step in and do some calls where we can help you connect to the cluster.
And then I just related it. For your licensing structure, your parallel toolbox, that includes parallel server, right?
No, so again, the parallel computing toolbox is a toolbox similar to all these other ones. Parallel server is slightly different. So parallel server would be done by the CHPC. They buy a number of worker licenses associated with that, and that's just run by the cluster itself. It's not going to be like a toolbox toolbox license in the same way. But the CHPC will take care of that for you. So the parallel server will be set up, and it'll just scale whatever MATLAB workflow you have.
Okay. So yeah. So obviously this wouldn't work on my personal machine because if I wanted to use, if I was using Apple, I wouldn't have any NVIDIA GPUs and how.
So yeah, so parallel computing toolbox, that toolbox allows you to access NVIDIA GPUs only. So that is correct that Apple GPUs are not made available through that. But if you had a personal work computer with an NVIDIA GPU, the PCT would allow you to use that. But yeah, as of right now, Apple GPUs are not made available through that.
Charles?
So on the topic of the NVIDIA GPUs supported on a workstation, all NVIDIA GPUs or workstation GPUs only, or server class GPUs only?
So if it's an NVIDIA GPU, it should be running. So we do like scientific and gaming GPUs are both fine. Whatever workflow may be constrained, of course, by your setup, especially your VRAM. But MathWorks, it works either way.
Samuel?
Yes, I'm interested on data store feature. Do you have a limit on number of files that you can read?
In the data
The next set of files.
in the data store.
Yes.
So the data store, you don't define. You can define it by the file, but you usually define it by the memory. So let's say you have thousands of files. You don't tell it to read in 10 files at a time. You tell it to read in X gigabytes at a time. So you would usually say like, okay, I want to read 1 gigabyte. So that chunk of data that you're reading in is 1 gigabyte, and then it does its operations, and then reads in the next gigabyte. You can define it by file if the files are, a good enough size. But yeah, typically you chunk it by the memory. Yeah.
Okay, thanks for those questions. There's no more questions online, so maybe, if you want to end off just on the quantum focus.
Okay, yeah. So just a little bit about what quantum computing is. So this is an emerging technology. So I want to be very clear, it is very brand new. It's basically, how do I use the principles of quantum mechanics to take advantage of basically what are called qubits to do calculations that you typically could not do on a CPU. So the idea, I want to talk about 3 little things. One is superposition. So in quantum mechanics, you can actually be simultaneously in 2 states. So the idea of superposition is fundamental to understanding quantum computing. The second idea that I want to go over is entanglement, which is basically you're putting the states of 2 qubits together at the same time. And then the idea of decoherence, which is effectively how you're losing information of the quantum state as you take longer to do these calculations. So the idea of quantum superposition is the typical analogy is Schrodinger's cat. So you put a cat in a box. At some time, there's a 50% chance that a radioactive particle will kill the cat. The weird thing is that when that time has passed, you're actually in a superposition of being both alive and dead at the same time. And it's not until the cat is observed where it collapses into a singular state, either alive or dead. So quantum mechanics is very weird in this sense, but the idea is that there's some wave function, let's say the psi, and it's in the superposition of being in a spin state 0 state and a spin 1 state. So it's both at the same time, not one or the other. So that's the first fundamental thing. And then the second phenomenon is that you can actually entangle particles together, which means what you do is you push these qubits together, and their states become intrinsically linked. And what that means is that classical systems don't behave like this, and they're no longer described independently from each other. And so that leads to this much, much larger 2n complex coefficients that describe these states. So for example, if I have 3 qubits, I'll actually have 2 to the n, which is 8 different coefficients that describe this wave function. So I can be in a different spin states, but I actually have 8 of these spin states that I need to keep track of, which means I can make much more complicated, much larger things than I would with bits, which just have a string of bits, just yes or no. The one problem with quantum computing is that if your quantum system is not perfectly isolated, the state can interact with the environment. So, for example, with some qubit systems, your qubits can go out of phase, or they can do a qubit flip, and then that system no longer stays the same, and your coherence is mixed, and your information is actually lost. So, unlike bits, which are very stable, your qubits can actually lose information if you let them sit for too long. So most calculations in quantum computing have to be done quickly so that your decoherence doesn't affect the actual calculation. So what we usually do is we describe this through like a block sphere. So the idea is that you have two different spin states. You have the 0 spin state or the 1 spin state. Your wave function's actually in some superposition of that, and then you can do some quantum gates. So these are operations which operate on the qubit and change the state. So for example, a Hadamard gate would put something into a superposition of states, and then you can do something like rotate it along the block sphere. So the idea then is with a multi-qubit, you can then you can entangle them, and then your particles, your state becomes more complicated as you entangle more qubits, and you can encode more information in a smaller number of qubits than you could with normal bits. So the idea is, how do I put these things together, and how do I do some sort of calculation with them? And so the idea is basically, just like in classical computing, you have all this logic that you come from classical computing gates. Can we make this similar logic with quantum computing gates? So if I entangle particles in a certain way, and I make a complicated wave function, which is dependent on 2 to the n qubits, can I then use that operation to do some sort of complicated algorithm, which I wouldn't be able to do with a classical computing machine? So for example, if I have like a really complicated molecular model that has tons of different electron states, can I model that in quantum computing where I can scale at the same level as that system that I wouldn't be able to do in classical computing because it would take too long, or it would be unreasonable to store that amount of data? So that's the premise behind quantum computing. The quantum advantage, so when we talk about quantum advantage, what we're looking at is what algorithms would actually benefit from quantum computing. So when you were talking about that 2 to the n state, are there any topics that actually benefit and can use those complex algorithms? And the 3 that are most commonly talked about these days is optimization. So, with a lot of machine learning or mathematical tools like in finance, you're trying to optimize some complex functions. Quantum computing could effectively help you optimize those functions quicker than you could in classical computing. In AI and machine learning, as you go to much larger data sets, you need something that can help you operate on those very large data sets or very large functions. That's a potential gain for quantum computing. And then molecular chemical simulation. So if you have some sort of quantum system like you would in chemistry or biology, quantum computing can help you because it can more realistically simulate those very, very complex states. So those are just a few examples of where you could potentially, this is still in development, but you could potentially gain on classical computing because you struggle with the large, complicated states. I'm not going to go too much into detail here, but just wanted to put here this slide. This is still a very large effort, and it's growing year to year. So I think right now, in 2023, the most recent estimate was that there was $36 billion worldwide being spent on this. So many people are investigating this. The hardware is getting a lot of investment, but also now people are starting to think about algorithms. How do I actually make software that runs on this? So there's now a push to more and more research in that sense. The technology is growing, so now we're talking about hundreds of qubits, whereas a decade ago we were talking about maybe a handful of qubits. So the hardware is advancing. It's getting to very large qubit counts. And then people are starting the quantum algorithm. So it's still in its infancy, but people are starting to publish paper about quantum algorithms and how they take advantage of quantum computers and how they actually are taking it to speeding up performance of certain calculations. So I just want to say, from MATLAB's perspective, we are not looking at the hardware side. The hardware side is, a few companies that they each have their own way. We're not in the hardware space, but what we're looking at is this software and then the talent space. So the idea is, hardware is existing, it's expanding as these companies, do more of their research and they make chips with larger qubit counts. But what we're focusing on is how do you actually write quantum algorithms that take advantage of that hardware? And so this is where our software comes in. MATLAB fits in this space. The idea is, write MATLAB code, you make quantum gate arrays in MATLAB, and then you could potentially run on the hardware of different resources. So for example, you can connect to AWS or IBM Qiskit, IBM resources and run on the quantum hardware using MATLAB code. So that's the idea of where MATLAB's fitting into this. We're also trying to work with the people in these fields. So it's a lot of academia. We're working with people in these fields. How do they integrate this into their groups? How do they integrate this into whatever hardware resources they have connections with? So the actual support package itself, the basic idea is you can either code or put in blocks, and you can build quantum circuits. So you basically fill in the circuit that you want to build. You can simulate that quantum algorithm locally. So basically, you just pretend you're running on hardware, and you see what the actual simulation looks like. And then you can plot the results. You can histogram the results. Or you can also connect to quantum hardware and then run your algorithm on those. So we do that usually through AWS or some sort of IBM resource. And that allows you to actually run your code on those quantum hardware resources and see if it matches the simulation that you're running locally. We usually connect through Amazon Braket or IBM Qiskit runtime services, but that's the general idea, is you can design quantum gate arrays directly in MATLAB. You can use whatever MATLAB code you typically run with. You can compare with classical algorithms through MATLAB, but you can actually run and simulate on quantum hardware.
Thank you very much, Chad. And I know you can go much deeper, but it just, I think, shows that MathWorks is focusing on supporting this say software and algorithm development as well.
Yes,
I think it's maybe a good time. The reason why I asked Chad to just say something about this is because there are some CHPC users that does not know that CHPC also provides a mechanism for users to get access to quantum computing. And we don't have, of course, our own quantum computer, but we have a contract currently that's active with IBM where you can get access to quantum resources, and this is something we intend to do in future. So wherever MathWorks comes into this, I don't know, but at least the users will then know. So maybe that's just something that users can take note of. Yeah. I'm not sure if there's any questions from the quantum computing side specifically.
Was there a question for them?
There was just, the question is there quantum, do you have resources of quantum machine learning? I think the question is more for CHPC. Do we have resources like access to computing resources? And that's basically what I'm saying. Whether you use it for quantum machine learning, I'm not so sure. I mean, it is a limited resource, so I advise if anybody wants to know more, please just contact the CHPC. Yeah. We can put you in connection with the people that can answer your questions. But at least the general answer is yes, we have access to quantum computing, and it is something that users can benefit from.
Yeah. And we also have examples from different quantum codes. So we have a quantum machine learning example. So if you want to try that, you can take it directly from our example page and run some base algorithms that way.
But I think we are running a bit out of time, and I think thank you very much, Chad. We should end it there. I want to thank all the people online. We've got 35 people online, so more than in the venue. Yeah. So we really appreciate the interest to also join the seminar. And thank you, Chad, for presenting this. It is very useful, and we are very pleased that you made the effort to come. So thank you very much. Just appreciate. Sure, I appreciate it.
Thank you.
There's also some clapping on.
Yes, I see a few hands over here.
Thank you very much to everybody that joined on Zoom, and that is, we will close the seminar now.
Thank you.